Welcome back everyone and welcome to the final topic of Unit 3 Chemistry. In the next 3 weeks or so, we will be looking at two aspects of any chemical reaction that you need to consider if you want to successfully apply chemistry to everyday life. And those two aspects are reaction rate. So basically you're trying to answer the question, I actually can't write, of how fast a reaction is happening. Can you make it faster? Can you make it slower depending on the type of reaction that you're talking about? You want to slow some reactions down if it is a side reaction that is competing with your main reaction. And then the second aspect of a chemical reaction that I don't think we have considered at all is the concept of equilibrium, or how far. Now this applies solely to reversible reactions, and there are some really interesting applications of equilibrium that we'll talk about in the next 2 weeks. But I think this week we're just going to talk about reaction rate. Okay, this is the agenda for today's video. Before we can even discuss reaction rate, it is important to go back and redefine what a chemical reaction is. And I just want to quickly discuss collision theory again, which is the theoretical framework under which you're going to base all of your explanations and predictions from. Okay, so a chemical reaction, this is one way that you can define chemical reaction, which is a process which involves a rearrangement of atoms. The exception here, of course, is nuclear reactions. Nuclear reactions actually change the nucleus, but we don't talk about nuclear reactions in BCE chemistry. So if I just give a quick example, if you have something like hydrogen and then reacting with oxygen, so this is also a redox reaction, and the product, well, you produce two water. You can see here that there has been a rearrangement of atoms. The hydrogen atoms are no longer covalently linked together, the oxygen atoms no longer covalently linked together, and because hydrogen now linked with oxygen to form water. So there is a rearrangement of atoms here. And the other thing that you need to know is that the conditions required for a chemical reaction to occur, so the conditions required for this rearrangement of atoms to take place, all of those conditions are called collectively as collision theory. Whenever you answer a question relating to reaction rate, or whenever you make a prediction, you have to base it on collision theory. You can't just say, oh, because I had a dream last night. So this is your theoretical framework. So let's just redefine what collision theory is. Okay, so let's say I have a simulation here, and the reaction that is taking place here is A plus BC. So BC is a compound containing B and C, and when they react, they're going to form AB. So there is a rearrangement of atoms. B will now form with A, and then you have C. So I'm just going to start by adding one molecule of A and one molecule of BC into the reaction chamber. So that's A, and then that's BC. So this is going to take a while, but hopefully you can see here that just because you add the two reactants together doesn't necessarily mean that they're going to form products immediately. The first thing that needs to happen, which kind of happened, but because the reaction chamber is really big and you really only have two molecules, it's very hard for it to happen, is you need the two reactants to actually collide with each other. So according to collision theory, in order for a chemical reaction to occur, the first thing that needs to happen is that the reactants must collide. They must meet. Obviously, this is a theoretical situation. You're never going to have two molecules in such a big space. So you normally have more molecules, and this is not a vacuum. Well, in reality, you probably don't have a vacuum, so you have gas molecules and this collision, but you need collision of the two reactants in order for the reaction to take place. So that's the first thing. So let's just keep watching. I think we're about halfway through, and so far I haven't got a chemical reaction. I think I got a little bit impatient and actually raised the temperature at this point. So they're going to move a little bit faster. Yep, so I've raised the temperature here. And it's still quite hard. Oh, so they collide again. So see how even though they collided, you still haven't got a product. Oh, now we got the product. Okay, so the second condition, and let me just go back for a second, is that even though they collide, that doesn't necessarily mean a product will be formed. The second condition is that the collision must occur with the correct orientation. So you can think of it this way. Essentially, in this particular example, the collision has to occur right here. So A has to hit the bond where B and C are bonding to each other in order for this bond to break and in order for new bonds to form. So you need to have a correct orientation of the collision, which is why these two need to collide a few times with different orientations, and then one of them actually get to the product. Now, I just want to talk about the correct orientation a little bit more. So this is another example of correct orientation using another chemical reaction. So in this particular case, this is an unfavorable collision orientation. So if the two reactants collide in this particular orientation, you you're less likely to have a successful reaction rate, or sometimes you cannot have a successful reaction if this is the orientation that the two reactants are taking. But this, in this case, is going to be a favorable orientation. So if they collide this way, it is more likely that they're going to form products. You don't actually need to know this, but I just want to show you because I really like the word. Steric hindrance is a concept that you're going to learn in university if you actually learn chemistry there. But think of it in the form that molecules and atoms are three-dimensional objects. So if, let's say, for example, you want to react to this carbon, this is a 3D model of what they look like. This is the ball, not the ball, it's the I forgot the name of this model. But anyway, so if you actually want to react to this carbon, it's actually very hard if you have the carbon in this molecule because of all the other molecules around it that essentially shield the molecule in the carbon atom inside. So this is probably like a more advanced version of correct orientation, but even with these molecules, you have to know where you're supposed to attack the carbon atom. Otherwise, you're not going to have a reaction at all. Once again, steric hindrance is not a VCE concept, but I think it allows you to see the importance of correct orientation a little bit more. So two conditions so far. The reactants must collide, but they also must collide with the correct orientation. The last condition we actually have talked about is when we talk about energy, is that the reactants must collide with enough energy to overcome the activation energy barrier. And this is the energy required to break the bonds in reactant. So if we go back to our example of A plus B, C, so these are the reactants. If you want this reaction to take place, the two reactants must collide hard enough to break the bonds in between B and C. So you have to break the bonds in reactants, so that, and then later on you form new bonds in products. So I could represent that change in energy using, you've seen this before, this is the energy profile diagram. I hope you remember. So the energy profile diagram represents the change in energy in the system over the course of a chemical reaction, and the vertical axis is the energy in the system, or enthalpy. So let's say we start around here. Well, try to anyway. This is like okay, I'm going to leave with that. So let's say this is A plus B, C. So in order for the reaction to take place, the system is going to have to absorb some extra energy, and that energy comes from the collision. So as it does that, it's going to increase. So this is the activation energy, which is the energy required in this particular case to break the bonds between B and C. And then once activation energy has been absorbed into the system, you basically get to what is called the transition state. So this is when the bond between B and C have sort of been broken, so there's a larger distance between these two atoms. And then if new bonds can be formed, that is going to, let's just make this an endothermic reaction. It's going to release some energy. So you have A, B plus C. So this is energy going in, and then this is energy is released from the formation of new bonds. Okay, so this is the last requirement. So you need to, there's those three requirements. The reactant must collide, and then they must collide with the correct orientation, and then they must collide with enough energy to overcome this activation energy barrier, or they must supply enough energy to break the bonds of the reactants, whatever way you want to word it. I just added a few slides here, which you can read in your own time, just of the definition of energy profile diagram. You should have seen this before. I think I drew this when we did energy profile diagram at the start of the year. And that's just another summary of exothermic versus endothermic reactions, but hopefully you still remembered energy profile diagrams and delta H as an indication. Actually, let's just go back. So delta H is an indication of whether a reaction is endothermic or exothermic. Delta H is going to come back in this topic. That's the nice thing about VC chemistry. Everything kind of connects. Maybe I give you a break from redox reactions for a bit, but it's coming back next unit. So anyway, so just to recap, if all three conditions are met, then the collision is considered to be successful or fruitful. I really like this word. You should all use it in your explanation. A successful collision is essentially that's when a chemical reaction actually occurs. So in other words, and I think I want to emphasize this point because I don't think not every student can appreciate this, is that just because you have a reaction mixture, so let's just say we have a reaction mixture here. So you have 10 atoms of A, and then you have 10 molecules of B. So just because you have 10 of A and 10 of B doesn't mean that immediately you're going to have 10 chemical reactions occurring. So not all collisions are successful. Most of the time they're not successful. Actually, only a small amount are successful. And they also do not become successful at the same time. So when I stop here, you already see there is like one product, but the rest of the collisions are still not successful yet. So things take time, and that's why we have to study reaction rate, because you need to know whether the amount of time that it takes to have a chemical reaction it's feasible in real life. I think that's it. Yeah, that is it for this.